Okay, so let's start the afternoon session. The first speaker is Dr. Ivan Arraut, and he will tell us about stability and predictability of the Schwarzschild-Dutta black hole in dRGT theory.
Okay, thank you very much, Professor Kawai. My name is Ivan Arraut. This is the title, as they say, Stability and Predictability of the Schwarzschild-Dutta black hole in the dRGT. These are extensions of a work which I did before in collaboration with Dr. Colamo. So, first, I want to mention the content. First, I will talk about the motivation and dRGT, some basic concepts. After, I will go to the Weinstein conditions. Then I will explain what the Schwarzschild black hole solution in the dRGT and what's the problem of predictability. After, I go to evaluate the motion of test particles moving around spherical symmetric sources. And I will talk about the conserved quantities. And finally, I will show the computation of the gamma function in the dRGT. And after I conclude, of course. So motivation, well, what was the motivation of the dRGT? Well, the dRGT appeared as one of the possibilities for solve the dark energy problem, which is one of the biggest problems in cosmology actually. Basically, our universe is composed of 60 or near 70% of dark energy, near 27% of dark matter, and ordinary matter only is near 5%. So that energy, the easiest way to explain the accelerated expansion of the universe is by introducing a cosmological constant in the Einstein equations. However, any theoretical attempt to reproduce the observed value has failed based on 0-point quantum fluctuations of the vacuum. On the other hand, we have, I will just mention briefly, we also have another problem, which is the dark matter, which is basically we cannot explain why the galaxies can be kept as a stable system, even if the velocity of the bodies rotate faster than what they should in order to keep the orbit stable. Also, we cannot explain the extra effect of gravitational lenses and what is observed in this, from the CMB. Okay. So let's start to explain what is massive gravity and the Einstein-Hilbert action. Basically, the Einstein-Hilbert action has a kinetic term of this form, and usually the root square of the determinant of the metric multiplied by a constant is what people call the simplest potential. It's just the cosmological constant, and of course, it's not massive. It's not a massive term. It doesn't satisfy the first Pauli tuning at first instance. So, if we want to introduce a massive term, we have to introduce a fiducial method. The first attempt to reproduce a massive theory of gravity was with the first Pauli, linear first Pauli theory, by using this first Pauli, this massive term, introducing, and by tuning the coefficients in this form. So you have a massive term given by this expression. And the Fell equations look like this. This is a ghost-free theory, but it has a pathology. The first pathology found in massive gravity was the BDBZ discontinuity. Basically, when you set the mass of the graviton to 0, you don't recover the massless theory. What you recover is a massless theory plus a scalar field coupled to the trace of the energy momentum tensor. You can see that in several ways, but the easiest way is calculating the propagators. You calculate the propagators for the massless and massive case, and after you ignore some terms which after contraction due to the energy momentum conservation they vanishes, and when you compare what remains, there is an extra force in the massive case, and this is the coupling of the scalar to the trace of the energy momentum tensor. So Einstein was the guy who proposed how to solve this problem. In 1972, he realized that the problem was that near the sources we have to take into account the nonlinearities. Okay? Basically, we have to recover general relativity near the sources, so that's the so-called Einstein mechanism, but in the original version of this mechanism, the World Desert Ghost is activated, and it was considered pathological, even if this precisely was the existence of the ghost who cancels the extra attractive effect due to the fifth degree of freedom. So after some years, then recently, actually maybe 4 or 5 years, Derang and Balassetoli, they realized that if they tune the coefficients, I mean, the problem of Einstein is that he introduced nonlinearity, but he kept the first Pauli tuning. So basically, he didn't introduce higher order terms in the action, non-derivative, actually, which are supposed to be the most relevant at the infrared. So the Ranga Balassetoli, they realized that if they introduce higher order terms and they tune the coefficients such that they group the ghost terms with new terms and they create a total derivative, then the theory becomes healthy and goes free. And still it has a Weinstein mechanism, and still it can reproduce the result of general relativity near the sources. Basically, this is the action they found. This is a potential which has two free parameters. And it depends on the dynamical metric and the fiducial metric through the Stuckelberg field. This is a ghost-free theory, and the field equations are given by this, which of course is the variation with respect to the dynamical metric. This is the energy momentum given by the variation of this potential with respect to the dynamical metric. And this equation can be obtained by the variation with respect to the Stuckelberg field, which is, and the unitary gauge is equivalent to the Bianchi identity. Okay? You can see more details in this paper with Dr. Kodama and me about this. So let's talk about Weinstein conditions. Well, I have found recently, not recently, I have followed these theories some years ago, not only these, other theories. I have realized that every theory trying to reproduce accelerated expansion of the universe reproduces at least 3 scales when the local physics is analyzed. The first scale is the gravitational radius, which becomes the event horizon for black holes. The second scale is the cosmological horizon, or the, let's say, the cosmological constant scale. And the third scale is a combination of both. Okay? This scale appears in the spatial de Sitter space, for example. It's the distance after which you cannot get bone orbits, for example. In dRGT, it appears in a different form. It appears at the Weinstein radius. This Weinstein radius is different to the Weinstein radius of the original nonlinear version of massive gravity. So one fundamental question is there any connection? Because it's accidentally, it's a coincidence. So what I try to find the way to unify, to explain this coincidence. So I derive what I call the Weinstein conditions. Basically, the Weinstein conditions means that if you have a dynamical metric and you work unitary gauge, all the degrees of freedoms are inside the dynamical metric. And the metric, if you assume that the metric is a monotonically continuous function, then at some level, the extra degrees of freedom will be relevant, and at that scale, the scale after which the extra degrees become relevant will appear as an extremal condition for the dynamical metric. So I have found that this is one way to find the Weinstein scale. In the case where the metric is static, this term vanishes and remains this. And these conditions, when applied to the dynamical metric in unitary gauge only, are used to evaluate the Weinstein radius. And it explains the coincidence because it is the way how it appears in spatial de Sitter, but it doesn't mean that it's the same. Both scales appear in a different way because both theories are constructed under different physical assumptions, but they have a common origin. I mean, it's an extremal condition. So let's go to the spatial de Sitter black hole solution in the dRGT. In the dRGT, we found this spherically symmetric solution with this in unitary gauge with this non-diagonal term, which cannot be gauged away because is due to the extra degrees of freedom. Any attempt to gauge away this term, you will just translate the degrees of freedom from the dynamical to the fiducial metric in order to conserve the some invariance of the theory. So we found this solution, and we found these are the components of the metric, basically. And the extra degrees of freedoms are introduced through the gauge transformation function, which is given, I will define later, is given explicitly by this function of R and T. And basically what deviate from GR is the dependence with respect to the position of this quantity. The dependence with respect to time, well, if you assume that this function is linear in time, which is most of the cases, there is no deviation with respect to ER in such a case due to the time dependence. This FR is just the standard, it looks like the standard spatial de Sitter function. The fiducial method, we are in unitary gauge, up to rescale is just given by this. So the stability analysis which we performed some time ago revealed that the solution with one free parameter was stable, with a functional degeneration appearing through the time components. I observed that in the case of scalar perturbations, at least for generic modes, after imposing the Bianchi identity, you can fix some degrees of freedom, but others remain free. And I have realized that the problematic components are the time components of the Stuckeler field. So this suggests, to me, I was concerned then to the conjugate variable, which is the energy. I was thinking, well, maybe there is a problem with the definition of energy in dRGT. So I began to review the concept of energy in such a case. And it can be seen, for example, the gauge transformation function. This is the gauge transformation function defined in this form. And this is how the time goes. The time goes in a spatial dependence and in a time dependence. And when the spatial dependence vanishes, of course, this recovers the natural role of time. So let's analyze then the energy in the RGT. Let's analyze particles moving, massive particles moving around a spherical symmetric source given by that method. So we have basically three conserved quantities. We have the Lagrangian of the particle moving is invariant. This is an invariant quantity. And is given explicitly by the other invariants are this: the energy, which I call this energy, and the angular momentum. It doesn't change because the metric in that part doesn't change. So this is in reality the conserved quantity, and this shows something. Precisely because we have a non-diagonal term in the metric, we have that our usual notion of energy is not conserved. Basically, it's velocity dependent. What is conserved is some extension of that quantity. So, if we write more explicitly this conserved quantity here, we find this equation. Well, in these papers, there are some typos mistakes in the right-hand side in this expression. I will correct within these days. But this is the expression, and basically, if you keep the usual notion of energy, of course, the degeneracy naturally will appear because you will have a velocity-dependent potential, basically, in this part. This equation basically reduces to the spatial de Sitter case when the spatial dependence of the gauge transformation function vanishes. So you just recover the previous equation. So as I said before, the extra contribution due to the Stuckeler degrees of freedoms are introduced through the spatial dependence of this function in some sense. Okay, basically what I said before is when this the spatial dependence of this vanishes, T0 recovers the standard rule of time. So there is no problem in the definition of energy in such a case. And this term would disappear. Basically, the standard notion, the usual notion of energy becomes the same dRGT energy. So as a motivating in that with that result, I decided to go ahead and evaluate the ADM and Komar mass functions in dRGT. I will show only the Komar mass function because I still evaluating. In principle, they should be equal if the time dependence of the fields at the far infinity are negligible. But I cannot guarantee that in dRGT. I would like to evaluate both. So the Komar mass function, basically, let's analyze the notions of energies in general relativity. In general relativity, in principle, if this is the time-like Killing vector, we can introduce this current. And it's conserved due to the Killing vector condition and due to the Bianchi identity or the energy momentum conservation. But however, this notion of energy is not good because, for example, when you work in vacuum, the energy momentum tensor is 0. So instead of that, we used to introduce this Komar, I think it was Komar who introduced this notion of energy, depending on the Ricci tensor. This is still the timeline killing vector, and this is conserved, a conserved current. And we can define then the energy as integral in the over the volume of that current. And after taking into account these operations, we can translate this integral in a volume by integral in a surface. Okay? N is basically a timeline vector, unit vector, and this is a space line. Okay? And this is the timeline killing vector. And there is some detail here how to calculate the killing vector. Well, if the space line is asymptotically flat, of course the normalization of killing vector is trivial. You just say that this gamma t is 1 when you are at the infinity. But if you have a Schwarzschild de Sitter space, it's not trivial at all because you have two even horizons. And there is no guarantee that your coordinate system is good enough when you overpass one of the horizons. For example, if you have a static metric, it's not static anymore inside the even horizon or outside the cosmological horizon. So I normalize in agreement with this condition. It's similar to what Bosso-Hawking did for the black hole thermodynamics in Schwarzschild de Sitter, but the difference is, in conceptual difference is that I evaluate the Weinstein radius. Because, as I said before, for me the Weinstein radius is the extremal condition for the dynamical metric in unitary gauge. And in addition, well, for evaluating this integral, I have to know if we know the normalization of this vector. This is -1 normalized, and this is 1 normalized. I can calculate these vectors. This is basically the induced metric. Is a square, so it's basically the determinant of that is to a sphere, and this is the timeline killing vector. And the timeline killing vector, even if you normalize, when you normalize, what happens is that there is a scale factor depending on the mass of the source, but it doesn't depend on the spatial components or so. So you can evaluate this expression exactly as you do in GR, because there is no spatial dependence here. So the contributions will come from the Christopher connections when you evaluate this covariant derivative. And, well, this is the value which I obtained for N0 and sigma r, which I will use there, YN0, because this is only the zero components relevant here. I'm sorry, this is R, and this is 0, 0. Yeah. And even if KR is 0, it doesn't matter because you have a contribution from the Christopher connection. So it doesn't mean that it's 0, this quantity. So you obtain these expressions through this normalization, and you just replace in this quantity which is inside the integral, and you obtain this expression. What remains here is to evaluate the Christopher connections here, and I did an assumption at this point. That assumption can be removed, of course. I assume that you can, after gauge transformation, of course, you can translate this metric to the static metric diagonal. Then, okay, it means that I can assume that the gauge transformation function is linear in time. As I say, when the spatial dependence vanishes, this recovers the role of time. And you can separate this in time contribution and spatial contribution. This contribution basically is what generates the deviation with respect to the GR behavior, and it contains the contribution of the extra degrees of freedom. So when you evaluate the Christopher connection, you obtain this. Gamma t is normalized in agreement with what I said before. This is just derivative with time, this is a spatial derivative with respect to r, and so on. So after introducing the determinant of the induced metric, you obtain this. This is the result. This is what I have called the Komar energy in dRGT. And Of course, this expression clearly depends on the dynamics of the Stucker field, and it reduced to the standard Komar function in general relativity when this vanishes, basically. And when this is linear, of course, when the dependence of time is linear, the dependence of this with respect to time is linear. And what to comment? Well, in principle, as I say, the Komar integral, the Komar energy and the ADN energy should be the same in principle if the background is static, and if the degrees of freedoms are time independent in the far infinity. But still, I don't want to guarantee that in this case. So the previous expression, this expression, the Komar mass, is satisfied when this condition, is well defined when this condition is satisfied. And I have found that this condition is perfectly satisfied with one of the solutions, the family of solutions obtained here, with two free parameters and the gauge transformation function fixed. For the other family of solutions, of course, with one free parameter and the gauge transformation function, one free parameter and the gauge transformation function free, this condition has to be taken into account. Still, for example, what remains to analyze? I have derived some conserved expressions related to the energy definition in dRGT. The energy in the standard definition is not conserved, it's a velocity-dependent quantity. The Komar mass function is modified by the dynamic of the Stucker fields. The further analysis are in process. I found recently that somebody claimed that actually the ADN mass is not conserved in dRGT, but they analyzed the linear theory. They introduced the mass term at the linear level, so there is no guarantee that the same behavior will appear at the non-linear level. It has to be evaluated, and that's what I'm confronting now with that result. Well, that's all. I could have included all of them. Thank you.
So questions or comments, please?
So in the linear theory, as you said, the reach time mechanism can be considered as the ghost degree of freedom, cancels the force of the fifth degree. In dRGT, there is no ghost, so how to intuitively understand the reach time mechanism?
How to understand the variation mechanism? That's a good question. Well, if there is no ghost, why still we can cancel the extra force? Well, it's due to non-linearities. Basically, when you calculate the field equations, let's say that you are in any gauge, and you calculate the field equations, variation with respect to the dynamical metric and variation with respect to the Stucker field. When you are inside, the equation of the dynamics of the Stucker fields have two contributions, one linear and one nonlinear. When you are inside the Weinstein radius, very close to the source, the nonlinear contribution governs the dynamics, and basically makes the dynamics of this Stucker field negligible. Basically, it's due to nonlinearities. When, in the opposite sense, when you are farther away from the Weinstein radius, the extra degrees of freedom become relevant. The reason is because the nonlinear term becomes negligible. So when the equation becomes linear and comparable in order of magnitude, these degrees of freedom of the scalar become comparable with the degrees of freedoms of the metric. So that's basically the reason. But as I said before, it can be seen also, well, at least the scale, I'm not saying the mechanism cannot be explained in this form, but the scale can be derived as an external condition of the dynamical metric in unitary gauge. That's not only intuitive, there is a proof behind that, so it's okay.
So any other questions?
Okay, it seems that the energy you define here is the energy of the test particles in massive gravity. Is there something? Is there a definition for the energy? For example, something like the ADM energy in GR.
Well, I evaluated two energies. First, I evaluated I consider invariant the Lagrangian of test particles moving around the spherical symmetric source. No? That's one invariant. And after, I demonstrated that that quantity is not conserved at all if we keep the usual notion of energy as a quantity which is concerned with the time translation. And after, in spite of that, then I decided to evaluate the other definition of energy. We have different definitions of energy. We have IDM, we have COMA. So I began to explore such ideas, and during the process, some colleague, actually for National Taiwan University, he told me that somebody had commented in this paper, actually, that ADM mass is not conserved in the dRGT, but I was checking the paper and they consider just the linear, I mean, not linear, but introduce the massive term at the linear level. So I want to explore what happened at the nonlinear level. There is no guarantee, and actually they assume asymptotically flat space, which is, in my case, I cannot assure, and there is no guarantee that your coordinate system is still valid at infinity. You have to prove that, for example.
Any other questions or comments? So,
you define the Kuma mass in terms of the peak translation of T, vector, but it's not a K vector for generic T0 values. So
yeah, exactly. If you there are two forms to evaluate. You can evaluate that form, and also you say that you have to say to.
For example, you can go to another point. If it's the matrix and take a standard
diagonal.
And in that case, of course, because K vector corresponds to translation of time.
Yeah.
But that K vector does not coincide with the delta T in the original coding. So you are defining some energy in terms of vector field, but it's not K vector. So
yeah, initially I wanted to explore the usual notion of energy, but actually you are right, because after I did the calculation, assuming that the Killing vector is pointing in T0 direction. And in such a case, you just obtain the standard result. You obtain just the common mass M.
So I'm asking why you use that definition. I mean, you think why it's meaningful?
Well, in order to explore I think that if you compare the notion of energy in the dRGT with our usual notion of energy is.
It's not conserved.
No, that is not conserved. But it's conserved when you consider the Killing vector in the direction of T0. That's correct. But I did it and you just obtain M. Unless I did something wrong. But I have to verify that part. I didn't show that part, but yes, I did in fact.
So any other questions? So if not, let's thank Ivan again.